everyone, in this video we're going to talk about the mole ratio and how to use this in chemical calculations and unit conversions. Oftentimes we want to figure out how much of a chemical is made after a chemical reaction happens. For example, this is one here where we have, say, glucose, which is sugar, which gets eaten by bacteria and turns into ethanol, which we're going to talk about a little bit more as a biofuel, and carbon dioxide. So this is a chemical reaction that happens in a bacteria, and it has certain products that these bacteria excrete after the reaction is done. So let's say that this is our balanced chemical equation here between our glucose breakdown and what it turns into. So if we start with 5.5 grams of glucose, if we put 5.5 grams and we feed it to this bacteria, how much ethanol can be made? So ethanol is a biofuel that we do use, and this is how we make it, is through bacterial conversion. So maybe we want to produce a certain amount of fuel, and we need to know how much glucose we have to start with in order to get to this. So we need certain information in order to do this conversion. So we're going to use what's called a mole ratio to figure this out. So let's say there's 5.5 grams that we put in here. So a mole ratio lets you compare amounts of one molecule to another. So this is really important. It's when we want to compare, say, one thing on the chemical equation to another substance. So it's when we're comparing substances. So it's the moles of molecule A per the moles of molecule B. So how many of these we have for every how many of these we have. These are given by the numbers in front of the equations. So right here, this is an understood one, we just don't write them. So for every one molecule of glucose, there are 2 molecules of ethanol. For every 1 molecule of glucose, there are 2 molecules of carbon dioxide, or 2 moles, we can think of it that way. We can also say that for every 2 moles of ethanol, there are 2 moles of carbon dioxide. So these are ratios. These numbers in front of your chemicals are telling you how many there are. So we've got 1 glucose molecule, and that gets converted into 2 ethanol molecules. Right now glucose because it's so big. So we have 2 of these, and we have 2 CO2s. So essentially what it's saying is this 1 glucose molecule here breaks down into 1, 2 of these, and 1, 2 of these. So it tells us how many moles of each thing there are. Now, you might be wondering, well, if we have 5.5 grams of this, why can't we just double this number and say that we make 10.10 grams of ethanol? There's twice as much, right? That can't happen. We can't do that because these chemicals have different molar masses. They weigh differently. So if you have 5.5 grams of this and it's a really heavy substance, if you just double that amount, you aren't going to have the same amount of a lighter weight substance. It's like trying to compare a piece of metal this size to like a ping pong ball this size. Like they just weigh differently. We can't make that comparison. So if we convert it to moles, now we can compare. So that's why we need this mole ratio, because we just can't compare grams to grams. It's just not going to work. We can't do this. That's not right. So we have to use our mole ratio because we can't compare grams. So let's look at an example problem of our mole ratio in action. All right, so let's go ahead and do this problem together. So if you have 5.5 grams of glucose, let's do the first step. I'm going to walk you through this step by step because I think you all have the skills and capability to do each step of these. All right, so 5.5 grams of glucose. How many moles of this do you have? So how many moles of glucose do you have? All right, so go ahead and use unit conversion to find this information. I've given you the molar mass down here so you don't have to go to the periodic table and calculate it. Let's take a look at how to solve this. So if you have 5.5 grams of our glucose, which is C6H12O6. We want to find out how many moles of glucose we have. We're going to use unit conversion to get there. 180.15. And we find that we have 0.03 moles of glucose. Okay, great. So now we're in moles. That's how many moles of this stuff we have. And remember, we can compare moles to moles. We can certainly do what I showed you last time, but with moles. So we can say that because we have 0.03 moles of this, that means we've now got 0.06 of this, because there's twice as much. We can make that comparison. We can't with grams. So this is what a mole ratio is. It's telling you how many moles of one substance, i.e. in this case glucose, you have in relationship to moles of another substance, i.e. in this case ethanol. And we have a 1:2 ratio. Let's do the next step of this problem. Okay, so I previewed what we're going to be doing here. It's very simple. We're just going to be doubling this number because we have this 1:2 ratio. Let me show you how to do this using unit conversion though, because this is going to be really important. I like to always do unit conversion so I don't make mistakes. So let's go to our 0.03 moles of our glucose. Okay. Using the moles from problem 1, that's this value, how many moles of ethanol can you make? Well, we know it's pretty simple here. We're just doubling that amount. But let's look at it using unit conversion. So remember, with unit conversion, we need to cancel what's on the bottom in order to get rid of it so that we end up with our new unit. Our new unit here, what we're trying to solve for, is moles of ethanol, so CH3CH2OH. Now you might think this is the same unit because they're both moles, but if we look here, they're different substances. So I don't consider these the same unit because they're different chemical compounds. This is moles of one thing, and we're trying to turn it into moles of another. It's going to be a different value. So when I write this down, moles of our glucose, C6H12O6, to moles of our ethanol, CH3CH2OH. Okay, now we put in our numbers. So for every 1 mole of glucose, we have 2 moles of ethanol. This right here is our mole ratio. So this portion right here is the mole ratio. You may want to write that down. That's what I'm referring to when I talk about that, is how many of these for how many of these, or whatever 2 chemicals you're comparing. So we know that we simply, in order to solve for our moles of our ethanol, we just simply double this number, 0.06 moles. So that's how many moles of ethanol we can make. Let's move on to the next portion of this problem. So if we have 0.06 moles of ethanol, we know that's how much we can make. How many grams of this do you have? We often measure stuff out via weight. You know this in the lab. We usually use a balance. So if we want to know how much we're going to actually make, we're going to need to go to grams next. Okay. So go ahead and solve this problem. Find out how many grams of ethanol you make using the amount of moles that you have determined. Let's take a look at how to solve this one. So 0.06 moles of ethanol. I always like to write down my substances when I'm working these problems because it just really helps me keep things straight and it prevents me from making mistakes. And I think it's really easy to just grab the wrong number and make mistakes. So that's why I'm very meticulous about this. So moles of your ethanol per gram. So this value we get down here, 46.07 grams per mole. This comes from the periodic table, from our periodic table. And if you calculate this value, we end up with 2.76 grams of ethanol. So that's how much ethanol we can make from 5.5 grams of glucose. And you'll notice that those numbers are very different. You can't just double grams. It's not going to work. 5.5 turns into 2.76. This is why we have to use moles. We just can't convert those values to each other. Okay, so you're going to need this information in order to do your lab this week. You're going to be looking at acid-base reactions, so your titrations like this one. So sodium hydroxide with HCl makes a salt and water. This is an acid-base reaction. And you're going to need to use mole ratios in order to solve these. So one, again, really helpful unit conversion tip that I can give you is when you use mole ratios, make sure you use the name of the substance in the unit like I just showed you. Be very meticulous about that. Let's look at a titration example and work through this together. So if we have 20 mils of NaOH is needed to complete a reaction with 10 mils of 1 molar HCl. So all of this belongs to our HCl, this belongs to our NaOH. What is the concentration of the NaOH used in this reaction? You'll first need to remember the concentration, what units that is in. Concentration is in molarity, which is moles per liter. So we're trying to find moles per liter of sodium hydroxide. This is what we're solving for. So at the end of the day, this is where we're going. So we need to know how many moles of NaOH we have and how many liters we have. So how many moles do we have? How many liters? We know how many liters because that value is given to us right here. We can simply convert this into liters. So 0.02 liters. That's how much we have. So that value is good. We're good to go. So in reality, we're trying to find how many moles of NaOH we have. And we can find moles of NaOH using our mole ratio. So this is our balanced chemical equation right here. For every 1 NaOH, there's 1 HCl. So this is balanced already. It's a very simple equation, which is good. That helps us a lot. So we're just going to look at the mole ratios of these right here. So if we know how many moles of HCl we have, we can figure out how many moles of NaOH we have because we've got a 1-to-1 mole ratio. So what we want to do is we want to find moles of HCl. So let's take a look at how to do that. All right, so I'm going to task you all with finding this information out. We're given two numbers we're going to need to use in order to find moles of HCl. We are given that we have a 1 mole per liter, that's this 1 molarity thing here, concentration of the acid. We're also given that we have 10 milliliters of it. So take these two numbers here and use unit conversion in order to cancel out units such that you arrive at moles of HCl. So give that a shot. Let's take a look at how to find moles of HCl. So if we have 1 mole per liter of HCl, and we want to find out how many moles we have, we're going to need to multiply by our liters because liters has to go. So we have 10 milliliters here, which converts to 0.01 liters. I divided that by 1,000 in order to get that number. So this is 0.01 liters. If I multiply that out in my calculator, I find that I have 0.01 moles of HCl. I'm going to write this substance down. It's very important when you're doing unit conversion so that you don't get mixed up with what substance you're talking about. Okay, so if we know moles of HCl, we can use our mole ratio to get to NaOH. So all we're going to do here, in order to solve this, 0.1 moles of HCl. We're going to use our mole ratio, 1 mole of HCl for every 1 mole of NaOH. Simple enough, which means that the moles of NaOH we have are 0.01 moles. And so we can simply solve for molarity by taking that 0.01 moles of NaOH. Notice this is NaOH. This is very important. I'm going to highlight this. NaOH matches with the NaOH volume. So both of these numbers here come from NaOH. We cannot use the 10 milliliters here. This 10 milliliters belongs to the HCl, so it must be in the HCl conversion. So don't get those things mixed up. Each of these numbers belongs to different substances, which determines where you're going to put them. So in order to find the molarity here, you would just take 0.01 moles of NaOH and divide that by 0.02 liters of NaOH to give you a molarity of 0.5 molar NaOH. That's how you would solve this problem. Let's take a look at an example where we don't have a one-to-one ratio and how that's going to affect our outcome. So this is another titration, H2SO4. This is our acid. This is our base again. Let's say we have 20 mils of this one again. We use 20 mils. And it's what's needed to complete the reaction with 10 milliliters of 1 molar H2SO4. It asks us, what is the concentration of the sodium hydroxide used in the reaction? So we're solving for the same thing. We're still trying to find moles per liter of NaOH. So let's walk through the same steps. If we have moles per liter, we need to find moles. We have our liters. Our liters is right here. So we have 0.02 liters of NaOH. And we want moles of NaOH on the top. So in reality, that's the number we're solving for because we already have this one. We're good. In order to find moles of NaOH, we have to know the moles of our acid because we're going to use our mole ratio to get there. Okay, so let's solve for that first. So I'm going to task you with the same problem. Take the 10 milliliters of your H2SO4 and your 1 molar H2SO4 and tell me how many moles of H2SO4 do we have? Let's take a look at how to find moles of H2SO4. So we're going to take this number and convert it to liters first thing because we have 1 mole per liter of our H2SO4. We want liters to go away, so I need to convert this. So by dividing this by 1,000, we end up with our value in liters, which is 0.01 liters. That gives us the same amount of moles as the last time. Okay, so we have the same amount of moles as last time. Awesome. Now we want to find moles of NaOH. So go ahead here and use this value and your mole ratio to find out how many moles of NaOH we have. Let's take a look at how to do this. Take 0.01 moles of your H2SO4. And we know that for every 1 mole of our H2SO4, we have 2 moles of our NaOH. Okay, so that means this number doubles. We now have 0.02, sorry, that's what this equals, 0.02 moles. 0.02 moles of NaOH. Okay, so if we solve for our molarity, that means our molarity is 0.02 moles of NaOH over 0.02 liters of NaOH, which means our concentration here is 1 mole per liter. This is different from last time. So we found 1 mole per liter here. Previously, our concentration was 0.5 molar. Okay, so by changing our ratios here, our mole ratios in between our acid and base, we find an entirely different answer. So that's why this matters, and why you're going to need to watch out for it whenever you're doing unit conversions.